This is a simulation of a basic conveyor system controlled by B&R hardware. I'm going to demonstrate voice interaction with this machine via a connection to a ROS network. Now, I decided to work on this because I'm passionate about creating bridges between existing technology sets, and the B&R and ROS ecosystems are really quite an interesting fit here. On the right then, I have a map view visualization connected to an ARsim instance running in the background. On the left, I have a Linux virtual machine running ROS. As you can see, cases are moving through the system from left to right. And when a case exits the system, as this blue one is about to do here momentarily, we're going to get a message over on the left published that describes what just happened. Blue case processing complete. So this kind of shows that we have some basic communication going on between the two systems. Now, all smart devices that consume audio require a wake command of some sort, and in this case I've implemented it as a button on the UI, right here. Once I press this button, I'll be able to issue voice command to the ARsim controller via ROS. So here we go. Turn on work light. Set speed to 0.2. Stop. Clear all cases. Jog conveyor forward at 0.5 meters per second. Place green case. Place red case. Turn off work light. Set deceleration to 0.2. Stop. As you can see, I just issued a series of voice commands that ARsim responded to directly, which is pretty cool. I have a machine, albeit simulated, that's responding to my voice. What I've really done here, though, is just leverage the strength of existing tools to create a useful feature with minimal effort. Amazon Lex and Poly, first off, are services in the AWS portfolio for creating conversational bots and synthesizing speech. So let's take a look at Amazon Lex first off. I have the console pulled up here, which is basically your IDE for interacting with Lex. And I'm going to zero in on this voice interaction robot, which I've created for this sample. Each bot can contain a number of different intents, and an intent is basically Lex's way of trying to extract meaning from an audio file. You'll send an audio file up to the cloud, and Lex is going to parse through it looking for one of these particular intents. If it finds something that's a close enough match, it will then return the corresponding info to the user via the SDK. Let's look at one example, for instance. Case locator intent is an intent that attempts to determine where a particular case is located. In this case, we have an additional parameter in here you can see that is not hard-coded, namely case color. This is Lex's ability basically to extract specific arguments from an audio file, which is pretty cool. You can mix and match these as you see fit, and you can define your own data types, which are called slot types down here. So here we've defined a slot type called case color, and it can take on values of red, green, or blue. Lex is then looking for one of those values inside of this sample utterance, and if it finds it, it'll return the full package to me. That's basically it. Lex can get more complicated, but that's all we're using right now. If we look then at Amazon Poly, this tool is a bit simpler. All we're doing really is sending a text file, or a string, I guess, and it's synthesizing it into speech, which would be an audio file that it then returns to the function caller. In this case, we're going to talk about how ROS is truly awesome, and Joanna, who has this pre-selectable voice down here, is going to tell us. So if we say listen to speech,
ROS is awesome.
Indeed it is. Now these two, Lex and Poly, are obviously very powerful tools, and AWS has released an SDK for developers wanting to interact with them. So on one side we have AWS, which is capable of voice interactions and is able to do a lot of kind of advanced voice interaction manipulations. And on the other side we have automation runtime, which is your standard real-time controller for an industrial machine. It has things like motion control, interacting with servos or other types of inverters, I/O control, data control, UI control. These are all kind of standard tasks that an industrial controller might have to handle. Neither of these two are particularly good at what the other one can handle. And so my mission or my objective with this demo was to try to tie them together. Now, the nuances of a full implementation for a voice interaction app are complex. First, you'd have to process the audio input. Then you'd have to implement a wake word, feed the data to AWS Lex via the SDK, receive a response, and process the response. All of this is somewhat involved, and it probably would have been a significant development effort with a steep learning curve if I'd had to start from scratch. Luckily, though, Lex and Poly are just two of a vast array of tools that have already been implemented in the ROS ecosystem as independent nodes. The ROS version I've used runs on Linux, which is kind of the foundation for our bridge. So we're going to stick this guy into our chart here. And within that Linux environment, which was the virtual machine we saw on the left, we're running the ROS core or ROS network. Now, what is ROS? ROS is a name that stands for Robot Operating System, but it's really a bit of a misnomer. It's not an operating system, nor is it just for robots. Rather, I'd say ROS is best understood as a collection of open source packages that communicate via a defined pub-sub mechanism. It's quite popular in academic circles and within tech startups, and is a really useful tool for basically spinning up some kind of an automated robotic solution very quickly by drawing on existing resources. It's not limited to those circles, though, and it's actually gaining a lot of traction in the industrial realm as well as of late. I would say one of its true strengths lies in its large network of collaborators across the globe. It really gives it a very bountiful portfolio of packages that you can select from. It's centered around the idea of independent nodes exchanging data over these well-defined channels called topics. A master node called ROS out here is responsible for spinning up all other configured nodes and setting them up to interact directly with one another. So here we have 5 other sample nodes that are shown inside of this ROS environment, and they're all communicating at first with the ROS out node. In this case, what I've done is just repurpose AWS's voice interaction sample app, which is something that they've made freely available online in one of their Git repos. And it contains all of the nodes shown here and a few more that I haven't listed. These nodes are written in Python or C++, and they do all the heavy lifting for us. Lex node and Poly node, for instance, are wrappers around the AWS SDK, and this allows them effectively to just communicate directly with their respective services. Voice input and voice output, on the other hand, are focused on interacting with your audio devices on your machine. So in my case, I just have my computer, my laptop PC's speakers and microphone that are being plugged into by these 2 particular nodes. And lastly, in this list, we have the voice interaction node, which handles the high-level processing and the moving of data back and forth between these other nodes. Now, these nodes are available publicly as open source packages because smart people have set it up and open sourced their hard work. And rather than reinventing the wheel, then, we can really stand on the shoulders of these giants and reuse the tools that are available. For me, the main challenge in developing this demo was building the bridge between the B&R and ROS ecosystems, given that all the rest was already kind of readily available here. This bridge was created using a ROS package called serial node over here, and I created my own driver within the automation runtime environment that would interface with the serial node package. The real strength that B&R brought to the table in this particular example is its ability to natively run standard C++ code on board. This allowed me to adopt another ROS sample, which is the one I just talked about here, to the B&R environment and set up serial TCP comms between ROS and ARsim. As a result, the B&R controller has direct access to all topics published on the ROS network and can conversely publish its own topics directly onto the network. So a quick example of what we're going to look at here is the Lex node, which would be receiving information from voice input that would probably go through voice interaction. But let's say voice input sends information through Lex node, which then passes it up to the Lex service, receives a response from the Lex service, and publishes the response as an intent structure. This structure is then available for our ROS node on the automation runtime side of things to subscribe to, and anytime the Lex node publishes that structure, it will be received by the ROS node. This is what we mean when I'm saying the kind of the independent pub/sub mechanism. Now, let's take a closer look at what's going on with this particular sample. I can get a list of all active ROS nodes by easily typing in the following. If I say ROS node list, this will then show me in the terminal all of the nodes that are currently running inside of this ROS framework. You can see the first two resemble those, or are exactly the same as we saw in the PowerPoint, Lex node and Poly node for interfacing with AWS. We then have ROS out, which is our core node, and serial node for interfacing via TCP with the ARsim. A few others that I haven't gone into here. Now, if instead I want to try to examine the data that's exchanged between these nodes, I look at what's called the topics. Topics are basically the unit that's being, or the type that's being used to exchange information via the pub/sub mechanism. So a specific node has the ability to publish on a topic, and another node can subscribe to that topic. If it does, it will then receive every message published by the first node. So in order to look at the topics, we can type out this handy command, and this gives us a full list of all the topics that are actively being exchanged and used within this particular system. Each of these topics has at least one publisher, or else it won't show up in the list, and optional subscribers, 0 to n, basically. So let's start off here by revisiting the first topic that this terminal was echoing, which was the case tracker topic. You can see it listed right here as one of our active topics. In order to take a look at what's going on with that topic, I can use the echo command, and I just specify the name of the topic. Now, we can go back and start our auto mode once again, and you'll see as these cases come through, we're now getting the echo for this particular topic, green case processing complete. What's actually happening here is that the ARsim is publishing a string to the topic called case tracker, and I'm just visualizing that on the ROS side, even though this particular topic does not have an actual endpoint or subscriber. Nobody is trying to respond to it. I'm just using it for demonstration purposes here. So this pub/sub mechanism, I'd say, is a real strength of ROS, and for our context here, it's especially useful to be able to have access to all of the topics within that pub/sub network from ARsim. Now that we've seen a basic example, let's look at a more interesting one. We're going to revisit the fulfilled command topic, which is something that we saw down in the bottom terminal here. So, in order to get the syntax right, we'll go through another ROS topic list. And the particular topic that I'm looking for right now is this one right here, voice interaction node fulfilled command. This topic encapsulates the response that AWS Lex sends back down after it has processed our audio input. The response is just in the form of a structure that contains a string with the intent name and then an array of string pairs that contain parameter names and parameter values. So let's see if we can show what this looks like. Forgot the echo. All right, so now we are ready to echo this particular topic if anything ever is published to that topic. Right now you can see we're kind of in a holding pattern because there's no active publishing going on, but I'm going to enable voice on the B&R side, and we should see something in just a second. Stop. Place green case. Move conveyor forward by 1.2 meters. Set acceleration to 10. Move conveyor forward by 2 meters. move conveyor backward by 2.6 meters. Now that I've disabled voice, let's take a look at what just happened here. You can see we had a series of commands that got streamed here in our bottom left terminal, and we'll take it from the top. The first one is called stop, and this corresponds to one of our intents in Lex. You can see we have it called stop here, and this could have been initiated with any of these three utterances: freeze, halt, or stop. The topic, though, called fulfilled command, just returned the name of the intent and this array of slots, which in this case is empty because there are no slots configured for this intent. The next one is a little bit more interesting. We have a place case intent that was detected, which is located right here. And this particular intent takes in one slot, namely the case color. So you can see here we have the intent name again shown as the first element in the structure, and then our array of slots shows a key, which is the parameter name, along with a value. This is then available for us to process in code, and I'll show in a minute what that looks like inside of Automation Studio. Looking at one more here, which is even more interesting, we have a distance move command, which takes in two slots. If we look up here, we see the first slot is the move direction, followed by the move distance. Move direction was determined by Lex to be forward, and the move distance was 1.2. So this kind of shows you how this information is encapsulated right now. And we're going to move on now to looking at Poly in just a bit, because so far everything I've shown has just been related to Lex. The tie-in with Poly is going to be generating speech from text. So I'm going to set up a new topic echo here for the ROS topic that I'm using to transfer information from ARsim to Poly. Once again, we'll call our handy ROS topic list, and I happen to know that the next to last topic in this list is the one we're looking for. So ROS topic, don't forget the echo, voice output node, speak, and we're now ready to display any data that gets published on that particular topic. So let's go back to ARsim and see what we can do here. Jog conveyor forward at 0.2 meters per second. Notify me when the red case passes the photo eye. Place red case. Set speed to 0.3.
The red case has passed the photo eye.
Excellent. So you can see that we have data that was displayed here because we were echoing a topic that got published to by ARsim. This particular data is actually just a hard-coded string right now inside of ARsim. And when I published it to this particular topic, the Poly node reacted automatically to it and synthesized corresponding speech, sending it back down to my audio output node and through my speakers. So that kind of shows you what it looks like to interact with Poly here in this context. Next then, I'll show a full cycle using both Lex and Poly. Let's go ahead and get set up with our proper nodes. So up top, I'm going to echo the fulfilled command. And down below, I'll echo the speech command. Jog conveyor forward at 0.516 meters per second. What is our current conveyor speed?
The current conveyor speed is 0.516 meters per second.
Place blue case. Stop. Where is the blue case?
The blue case is 2.75305 meters away from the infeed.
In this example then, I subscribed to the fulfilled command topic up here, which is the one that's coming from Lex. And you could see I got some questions, for instance, some intents, that came through. For instance, case locator, which was me asking it where that particular case was located. And then once I received that case locator intent inside of ARsim, I processed the data and published to the speak topic. Down here, I published the blue case is at this position with probably more resolution than was necessary. This just shows
the blue case is 2.75305 meters away from the infeed.
And you can see my enable voice wake word is not fully functional because it's still listening to me. Now that we've covered several use cases, I'll show you how the Automation Studio project is set up for each of these. Let's pull this up. I currently have two tasks. The ROS task is written in C++ and consists of all the low-level hooks to establish communication with the ROS ecosystem. I can expand this out, and you see that we've got C++ and a bunch of .h header files in here. The main task, on the other hand, is written in structured text and handles all UI and motion-related activities. Main receives information from ROS via a global structure called ROS command. That's shown right here, which is basically an IEC translation of the fulfilled command topic that we were looking at inside of Linux there. This particular action that I have open here shows the syntax for responding to a command. So just as we saw by echoing the fulfilled command topic earlier, we are able to extract different intents and respond to them in code rather than just publishing them, or I should say echoing them inside of a terminal. So if we look at, let's say, the top one here, this is a good example to start off with. The ROS command.intent name is called work-like command, and this corresponds to this intent right here in our Lex console. You can see it get triggered by this following verbiage right here and has a single slot. If we detect this intent name in our logic inside of Automation Studio, we then take a look at what the value of the slot is, and depending on whether it's on or off, we're going to issue a command locally to turn on or off this particular I/O point. Next one is a little bit more interesting because we've got multiple slots in use. The jog move intent that we have parameterized somewhere here, there it is, takes in two different slots, move direction and move speed. And you can see once I receive that intent, I look for the direction, forward or backwards, and convert this into a command that I can send to the map access block. And then I set the speed based on the second slot, sending a command to move velocity of true. So that kind of shows how things are working inside of this action. And if we look a little bit closer at the ROS task, as I mentioned a second ago, this has many dependencies on various .h files. Some of these were converted from the ROS serial code. It's a specific node called ROS serial node, actually. And others were added to create the fully functional bridge between ARsim and ROS. Many of them as well are simply defining topic types that can be handled by ARsim. So if I expand out this stdmsgs, this string.h just allows me to publish to a simple topic whose only contents are a string. And that's the topic that I was using in publishing the poly command, for instance. If we look a little further down, we have this package, which has a fulfilled voice command.h file. This is just the header file that defines the structure that we used to process those fulfilled commands. And this is the actual structure that I'm converting over to a ROS command IEC struct. That's basically it. That gives you the full overview of my integrated voice interaction app. The ROS ecosystem is vast though, and there are many other packages that could open up new avenues for PLCs. So for instance, we've got something called gazebo simulation, which ties in directly with ROS. This is a 3D simulator environment that includes a physics engine and the ability to plug in various sensors with actual sensor feedback. We have things like vision processing packages, OpenCV, interactive markers. AWS recognition is another tie-in with an AWS service. Obviously, recognition is the facial recognition service that AWS provides. AWS SageMaker, this is a really cool one that does all the machine learning. Again, these recognition SageMakers come with their own SDKs, but it's a lot of work to integrate that into a B&R application. It might not even be possible given some C++ dependencies. So we could then just use the package that already has the SDK inside of it. And with SageMaker, you can do things like reinforcement learning. You could create some kind of autonomous agent and allow it to explore inside of an environment and kind of train itself as it goes. Next, then we've got a whole portfolio of drivers for ROS to communicate with external devices. Things like LiDAR drivers or lasers, 2D or 3D camera drivers. A lot of these are more customized or tailored towards specific robotics applications, but they're not limited to that in scope. These that I'm showing down at the bottom are kind of the more specific robotics ones. We've got drivers for interfacing with a host of different drones that are on the market, the ability to implement autonomous navigation for independent agents, and SLAM, which is simultaneous localization and mapping, obviously very important if you're trying to navigate through an unfamiliar environment. 3D point cloud library is another popular one, or a basic one obviously is coordinate transforms. So just wanted to give this last picture so that we could get an idea of how vast ROS really is and what the potential benefits could be of more fully integrating some of these packages into the industrial automation realm. Thanks for watching. If you enjoyed this video, please like or comment, or feel free to reach out to me directly with questions or feedback.